Thank you. Hello everyone. I'm Alex. I'm going to talk about WebAssembly. Just the first short question, how many of you have used WebAssembly? Okay, so we're good. How many of you have used WebAssembly Components, the component model? All right. So my talk is useful, hopefully. I'm going to talk about plugins. So plugins, or more recently extensions, are pieces of software which make our applications richer. Usually if you have an application, you would like to build an ecosystem and you would like to open up APIs so the community can contribute and enrich it. Almost every application that we have, not on the phone but on a PC, supports extensions in a way or another. So what are the requirements for an extension for an application? First of all, the best thing would be if we could write extensions or plugins in any language that we like. And this is usually not true. Usually extensions today have to be written somehow in the language that the application has been written. They should run fast. So if I write an extension, it should not hinder my application. And ideally, it should run sandboxed. So an extension or a plugin is not able to stop my application or make it misbehave, so on and so forth. Another thing is the provider of the extension might not want to reveal the source code. So for many applications today, they're written in the browser or in a software that simulates the browser. The problem that extension vendors have, they somehow have to ship the source code. Maybe minified, but some people were not really very happy about this. And actually, running plugins boils down to running third-party code in your environment. And so far, these are the ways which you can write extensions for native applications. So for JavaScript application and the browser application, yes, you just write some JavaScript that you load. But for native applications, these are the ways. Either use the C ABI, so just make a shared library. And this is the old classic way of writing plugins. It works in any compiled language. Any language will be able probably to export the C ABI. It's super fast, but it's not sandboxed. And there's a lot of problems with shared libraries. You have to get it right. And the problem is the library cannot tell you anything about what's happening inside. You just see a C function header, you hope it's correct, and the library does whatever it wants. The second way, on the other side, is writing extension in a scripting language. And Lua is one of the favorite ones, and JavaScript, embedded JavaScript engines. They're sandboxed, and they're super portable, but they're slow. I mean, 10 times slower than compiled code. And the question that we have is there any way to write Rust modules? And the answer is, they're fast. They're kind of sandboxed because you have a borrow checker, which usually should agree with you that your extension doesn't do really bad things. But the problem with Rust is it has no stable ABI. So while the type system and everything is super nice, and it's a huge improvement from what we had before, it can't export it. So if you want to write a module in Rust and share it in binary form, you have to make sure that the other person using it is using exactly the same compiler. And it's not the same compiler version, it's the same compiler hash. Because from a minor version to another minor version, the ABI, the way Rust represents data, can change. I think there's some effort in the Rust project to stabilize an API, but probably that's still far away. So this implies that if you want to write Rust plugins, you either export it as a shared library, and we boil down to C, or the compiler has to see the whole source code. And at least in industrial environments, I had several questions, like, hey, we have a super nice algorithm, we want to share it and sell it, but we can't reveal the source code. It's a patent on it. So this is the status today. The question is, who runs really fast, untrusted code? And the answer is the web. they have been doing this for 25 years. Because if you think of it, almost everything that you use in the browser, your email, your calendar, and unless you have a specific app, you will use the browser. And these guys are experts in running third-party code really fast. And this is in part due to WebAssembly. So 8 years ago, they realized that there's no way we can optimize JavaScript anymore. I mean, of course, we can get 1, 2, 3% improvement. But due to the way in which JavaScript represents data types, it's impossible to optimize. So they found WebAssembly, which is actually compiled JavaScript. So what if we had a pseudo assembly language in which we can compile anything like C, Rust, Java, Kotlin, whatever, and then the browser can optimize that code. And this is WebAssembly. It's a standard bytecode, and I mean standard, it's not the first bytecode. We have .NET, we have Java, but it's not actually a standard. There's companies behind it. This is a community effort. And WebAssembly has been written with safety and efficiency in mind. The code in WebAssembly needs to be formally verified before it can be run. And you have to think of it as a bytecode for a processor which knows what a function is. Because processors actually don't know what a function is. They just do jumps and maybe keep in mind the return address. And this was done for the web. And this is what we call today WebAssembly Core, and I'm assuming this is what you used. So it's built to optimize slow JavaScript code. The idea behind was actually, what if we could write some C code which is fast and run it in the browser? And a very good example of WebAssembly is syntax highlighting. It's not written in JavaScript. It's WebAssembly modules. And it provides a C-like ABI. So you can transfer between JavaScript and WebAssembly numbers. I mean, it's super strongly sandboxed because it runs in a browser and it's binary code that they need to run on your computer. And the question is, who doesn't like to run Doom in a browser? I'm sorry, QEMU. This is one of the examples that we have. And then the question is, okay, so if we can run C apps in the browser, why can't we go outside? Because Node.js did this. So meet WASI, WebAssembly System Interface, preview number 1. The idea was, what if we can compile applications to WebAssembly and then run them on computers? And expose some interfaces for them so they can access files and networking and everything in a secure manner. And a lot of languages added support to WebAssembly, and Rust, due to LLVM, actually has 2 targets for this. One is WebAssembly 32 bits, only 32 bits for now, unknown unknown. This is basically the WebAssembly module. It's just processing. It has no support for files, for networking, anything. You can run things fast. And it's your job to export functions to WebAssembly. Or WASI32, WASI preview 1. This is libc for WebAssembly. So in Rust, you can write a normal application with the main function, standard library, compile it for this target, and then you can run it on your computer. Of course, you need a host to run it. A host is a piece of software which loads the WebAssembly module, verifies it, compiles it, and then runs it. And it runs it in a controlled manner. You can actually specify to the host which part of the file system is available, which networking addresses are available, what can it do with the clocks, and so on and so forth. And these are some of the languages that support WebAssembly targets. So you can build WebAssembly core modules. Rust, C and C++ through LLVM. Kotlin has an experimental support. Yes, you can write Kotlin apps. Java under T virtual machine, Go, and JavaScript. You can write JavaScript and compile it to a module. It actually embeds Starling Monkey, which is a version of SpiderMonkey, but which runs super, super fast. Now, to run the module, you need one of these. Either the browser, browsers will run WebAssembly modules natively, but through the browser, there's no way you can get to the platform. You can't get to your files, you can get to networking, but that's all you can do. Node.js and Dino can do this. Of course, it's the same engine from the browser. Wasmtime can do it. This is a Rust project, which is based on CraneLift. CraneLift is a compiler, a backend of a compiler, and through Wasmtime, you can run WebAssembly modules on your computer. And Wasmtime is shipped either as a command line application, so Wasmtime your module and it runs, or as a Rust crate. You can build your own software, include the Wasmtime crate, instantiate modules, and run them. So this is super, super nice. Another one is Wasmar, same as Wasmtime. And we have WAMR. This is a reference implementation of an executor for WebAssembly. It's written in C. It doesn't compile. It's slow. But it is the reference implementation. And while these executors work on the main architectures, this one works on anything, including small chips. So we have run WebAssembly components on a 64K of RAM. Of course, it's slow. It's 10 times slower, but it works. We are going to use today Wasmtime. So here's a case study on how you can write a plugin in WebAssembly. I think that they call it Zellij. I'm not sure exactly how to call the name, but IJ in Dutch I think is I, so Zellij. This is a terminal emulator, terminal multiplexer. If you know Tmux, it's an alternative to Tmux. So it's a terminal emulator, and they support WebAssembly plugins. So if you want to enhance it, write WebAssembly. They use the WebAssembly core. So that means that they are having a really hard time transferring data. So if you will build a plugin, you write the plugin in Rust or C or Go. You will have structures, you will have enums, you will have strings. This is difficult to transfer. I mean, it's really, really difficult to transfer. So what they do is they pipe it. So they have the host, which is the Zellij application. Then they have the plugins, which are WebAssembly core modules. And if they want to ship data in between, they basically start a new process for every plugin and use the pipe, the system pipe. The plugin reads from the standard input and writes to the standard output, and so does the host. And if the plugin needs to display something on the screen, it just displays on the screen. Every plugin can use its own standard library, so plugins are rather big, because when you write the module, they need to ship it with the whole standard library. They can't provide it to you. And but they can be written in any language. This was one of the first projects which was more or less mainstream, which used leveraged WebAssembly for plugins. This is how it looks like. So if you want to write a plugin for Zellij, this is the API that they expose. And you can see they have B trees and strings and pipe messages. So this is what you see. Because for you to write a plugin, you will import a crate. Now what the crate does is this. So no mangle, this means C names. No mangle, no mangle, no mangle. They read from the std in a protobuf and then deserialize data. This is slow. I mean, they go through the operating system, everything. So every data object that needs to go to the plugin is completely serialized into text and then deserialized from text. And if they want to determine the version of the plugin, they actually make the plugin print it on the screen and they read it. But don't get me wrong, this was cool. I mean, this is an older project. It was super cool. So the question is there any way to share data between WAS modules? And the answer comes from the WebAssembly component model. This is preview number 2, WASI preview number 2. It has been stabilized last year, I think in November. Maybe I'm wrong about this. So, writing WASI was a super challenge. The standard library of languages is full of strings, is full of shared data. If you have libraries, you have a piece of software that needs to combine these libraries, this becomes super, super difficult in WebAssembly. Because it was written, the core WebAssembly was written for fast computation, not for sharing of data. So how can we link modules together? How do we share the memory? Each WebAssembly module has its own memory. If you need to share memory in between, how do you do this? If one of the modules modifies the memory in a bad way, the other one crashes. So this is bad. And how do we make sure that all the modules have the same data representation? How do we represent a string? How do we represent a structure? Is it a null terminated string? It's a Java string. How do we do this? What's the format of the characters? Is it ASCII? Is it UDF-8? That's a good question. And I remember trying to do this in 2017 when we figured out, hey, maybe we can use it for a computer, and these are the challenges that we faced. And incidentally, the WASI team faced the same. So the WebAssembly component model tries to solve this. It defines a language, an interface definition language, which is called WIT, WebAssembly Interface Types. It defines a set of data types which can be shared in between modules. And it defines linking rules, how these modules should be linked together. The theory is super, super long, so it's like 50 pages probably of explanation, so I'm going to try to summarize it and give you a small head start into this. The main goal somehow is write it once in any language, link it to other components, and run it everywhere. So if this thing flies, developers should be able to be completely language agnostic. You can build an application that has a module written in Rust, one written in Go, one written in JavaScript, the other one in Python, and they should be able to work together nicely. And this is a personal opinion, this has the potential of becoming the main way of distributing applications. Because if you think so, imagine Linux applications. If it's in the distributions repository, it's fine. But if you need to compile it or ship a binary under Linux, it becomes a container. Oh, we don't ship the binary. We will ship everything around the binary. Libraries, configuration files. That's what Flatpak does today. It's more or less a container. But if this works, you can always ship applications in WebAssembly. You don't care about the operating system. You don't care about the libraries on the operating system. You just care that you have an executor. And Wasmtime is a good executor, and it works on most of the platforms. So WASI preview number 2 for Rust has this target. It has been stabilized very recently, so it's Rust 1.82. So this is really, really new. We can use Rust to build safe plugins and share meaningful data easily, and it's super sandboxed because it's WebAssembly. So let's take a look on how these interfaces look like. So the WIT file and the types in the WIT file were inspired by Rust. So first of all, you need to define interfaces. While you can import and export functions for legacy reasons from the core module, the recommendation is components export interfaces and import interfaces. So this is how you define an interface. Interface name. The case is kebab case, I think. So it's lowercase letters with minuses in between. And this has been selected on purpose because this will be transformed in Java into camel case, in C into snake case. Rust is going to be camel case depending on what that name is, or snake case. So if it's an interface, it's going to be camel case. If it's a function name, it's going to be snake case. So to make it completely agnostic, small letters, lines in between. Enums. Enums are the enums of C. So it's just a sequence of items, no payloads, just like that. As you can see, file, folder, link, and unknown. Enums are defined within interfaces. You can't define enums outside. So interfaces contain these enums. The second data type is a record. If somebody did Pascal, this brings up memories. So records are structures, but without methods. Actually structures. They can define fields, and they have a name. I have a typo there. Kind should have been with small k. I think my editor capitalized. So no methods, just plain data objects that can be shared. And variants. Variants are Rust enums. Enums with payloads. The representation in C is actually a union with a discriminant. So it defines a structure with a discriminant and then a union. In Rust, it defines an enum. But clearly, this was inspired from Rust. So you have variants, records, and enums. These are the data types that you can, the compound data types that you can ship. Of course, you can ship numbers. So U64, S64, U64 is unsigned, S64 is signed, and you have strings. The type string actually exists, and it's an UTF-8 encoded Rust-style string. Resources. Resources are objects with methods. So resources are an object that lives somewhere, has this interface, but it has no fields. The fields are completely opaque. So an interface that defines functions is basically a trait with static methods. A resource becomes a trait with methods, with self. It can have a constructor. I didn't list the constructor here. Resources can be owned or borrowed. And if you look here, when you return a resource, and I think parent returns an absolute path, which is a resource, it's an owned resource, always. But when a method takes a parameter or an argument with a resource, it can be owned or it can be borrowed. If it's owned, the host executor knows it needs to destroy it when the guest drops it, when the component drops it. If it's borrowed, it's a different story. Usually for functions, this will be borrowed. You can't return a borrowed resource. That doesn't work. Resources are managed by the host. So this was inspired from file descriptors. So whenever you need to create a resource, you basically create an ID. The WebAssembly component will get an ID which is unforgeable. Every time it needs to call a method, it will ship the ID and the method. And the whole life cycle is managed by the host. So that's why this has no fields. Within the host, of course, you can implement it on whatever you want. And the world. The world is what a component sees. So you can define several interfaces, and for several components, you can have different worlds. And the world basically defines which interfaces are imported from which interfaces are imported by the component, and which interfaces are exported. The imported interfaces, so VFS host, virtual file system host, is the interface that the component will use to do its job. So the component will call the methods there, or the functions. And the host will call the methods and the functions from VFS. That's what the component exposes. Of course, the export from one component can be connected to the import of another component. And then components call each other. This one imports and exports one. So this gets me to my example. How do we build an extension? And this will be a really, really quick tutorial, and I'm going to try to explain my experience in building this. If you remember the classical commander, I just called it junkyard. It's old. As you can see here, you can see it on GitHub, so you can see the full source code on GitHub with less comments than I would like, but I'll add the comments. You can see you have 2 panes. Every panel uses a trait to get the file system. On the right side, you can see a WebAssembly component written in Rust. On the left side, you see a WebAssembly component written in JavaScript. So this is in JavaScript. Everything here compiles to binary, and the WebAssembly components compile to WASM files, full binary. Nothing is source code. So let's see how this works. The tooling that you need to do this is in its infancy. So tools are great, but not stable usually, so things might change in the future. It's gonna stabilize eventually. It's way better than a year ago, but it's changing. So first you need with bindgen. This will generate the guest interfaces. It takes a with file and generates the guest code. It can dump Rust, C, Go, and C# and Java, except resources. So if you want to dump to Java, I wanted to make a component in Java, it will just panic with not implemented. So when it gets to resource, it's not implemented. So with bindgen is for the guest, for the plugin. Wasmtime is the executor. This is the crate that you will load in your Rust program. This one knows how to generate the host part of the component. So it has a macro, which is called bindgen, takes a with file, generates the traits. Cargo component will be the thing that will build your components. So you have the host application, and then you have a separate crate for every component. Until Rust 1.82, because it didn't support preview number 2, Rust cargo component was the only way. Rust would generate a WASI P1, and this one would adapt it to being a component. Now you can do this natively if you compile it for this target. So cargo component is still good. You still need it to generate some guest traits, but you can go around that without it. And JCO. JCO is for building components in JavaScript. So this is optional. This was just show off. Then you need to define your with file. It needs to have a package, because actually you can push components to repository. The package is namespace, column, component name, and optionally and version. You can't do it like in Java. It can't be a long thingy. In my example, I defined the VFS interface. This is what my plugin exports. So I defined the data types, the seek, the kind enum, the stat record, which says the size of the file, the kind of the file, and the file resource. The file resource has the functions for reading, writing to files, opening files, so on and so forth. And I have another resource, which is the file system, which basically contains the readdir method. So if you want to read the directory, just read the method. I didn't put a path as a string because I want to make sure paths are normalized and I don't have really crazy double dot or dots in the path. So I defined a resource which is called absolute path, and the function to create it, I could have done a constructor, but yeah. To use the absolute path, I need to import it into this interface. So I'm declaring it here because the path actually needs to be implemented by the host, but I can use it here. The use statement is strange. I mean, you need to put the name of the interface, dot, and then braces are compulsory. This changed a lot. During the last 4 years, the spec for the width file changed every month. So now it's stable. And then I define the world. The world is VFS plugin. I import VFS host, so for whatever the plugin needs from the host, and it needs the absolute path, because the host can create the paths, and it exports the VFS. You can find on GitHub the full file. If I had several types of plugins, so virtual file system, editor plugin, syntax highlighting for files, I would have a lot of interfaces and several worlds. And then for every plugin, I would tell the compiler, this is the world that you need to use. So this is step number 1, define this file. Step number 2 is create an API crate. So we're focusing on the plugin. On the host. Wasm-time component bindgen will create all the crates, all the data types and the interfaces that you need to load a plugin. It will have the data, the plain data types, so the enum, the variant, and the record. These are simple Rust structs and enums. That's super fine. Why do you need a separate API crate? Because these data types you will need in both the host and the plugin. And if it's not the exact same data type, and you generate this in 2 separate crates, Rust will complain because they look the same, but it's a different type. So you need to have the different type. Then this is how you generate it. So you take the width file. Make sure you derive additional traits, because on these things here, you might actually need equal, partial equal, and stuff like this. Make sure you add them here. So derive as many as you can, because you really don't know what you're going to use. And this gets tricky. For every resource, make sure you specify your own data type in the host. If you miss this, if you look on GitHub, go a few commits back. This becomes increasingly difficult, because what bindgen does, it defines a type which is an empty enum, which is an unconstructible type, and you will have to do a lot of things to actually link it to a type of yours. Of course, this is not documented properly. So I was writing the plugin, and I was like, this is too complicated. Like, why is this so complicated? And like digging into the source code of WASI, hey, whoa, what's this line here? So that's what it does. So this is important. So every resource, make sure you map it to a type in the host. That's the part. Okay. So going back to the width file. It's the package of the width file, which is junkyard VFS, column VFS plugin. And you see it here, the package. And then it's the interface and the resource. So the resource was defined in VFS host. And this is where I defined the absolute path. I skipped the methods because the code was too long, but it basically has the methods. So thank you for the question. I know it's strange. I mean, for me, writing this, it was like going through the source code, seeing, hey, how did they do this? So this is step number 2. Make a crate. This is the whole file of the crate, whole librs. Export these and do the other thing. And if you have custom types, you will have to define them in this crate. If that custom type is in another crate, most probably you will have a circular dependency. Because that crate where you have defined that type needs this one. But this crate needs the other crate to list the type over there. So for now, there's no way around it. The place where you define this bindgen has to define the path. Otherwise, you get into circular dependency. Step number 3. Create a trait for the plugin engine. Now here's the problem. BindGen creates the traits for the interfaces, but they look terrible. Like terrible. If you want to use it within your software and want to access this, you will want this. Because you will want the functions to actually have the absolute path here, the actual string, a result that you want. This is very, very similar to the guest trait that is being generated. The problem is I can't use the guest trait here because it's a different software that generates that guest trait, and the data types are not the same. They look the same, they have the same name, but Rust complains. So for now, you need to define your traits based on the interface. So whatever Rust generates is not really readable. It looks like bad. This is what Rust generates. So readDir looks like, this is what Rust generates for the host. So for every function in your interface, it generates a function call _ your function name, maybe with async, if it's an async one. You need to supply the store, the plugin, and the resource. And this is something that you don't want to do. I mean, you do it in your glue code, but you don't want to do it in the part of your program that uses the plugin. So this is why, for now at least, you have to do this. I know there's an effort from Christoph here to actually do symmetric traits. And they should merge this, but for now, there's no way around it. Tried everything. So this is how it looks like. You implement your own trait. You get the data store, and you call this one. So this is how readDir would look like. Get the store. The store is an object that you define when you start your wasmtime runtime. You need to get the ID of the resource, then call readDir, because readDir gets an absolute path, which in fact it gets a number. It gets the resource ID on which the plugin will call the methods to find out the path, the file name, the type, and so on. And you need to be careful on the lifetime, because I'm creating a resource here, borrowing it to the component. Make sure you delete it. Otherwise, you're leaking memory. Sadly, this takes me back to C, memory management. For now, this is how you have to do it.
I'm curious about why you're dereferencing the store and borrowing.
I think this is not the actual store. This is something off store. If I remember correctly, that's something off store. You need to deref it and then get a reference back. Yeah. No, I'll tell you why. My trait is self, and also my trait is send_sync, because I need to use it everywhere in my program, and I don't want to care about if I send it through threads. The store is not. And that's a mutex guard over there. So I have a mutex. When you get store, it locks a mutex, gets the store, and yeah, that's what happens. And actually, the thing is, I can run my plugins on separate threads, each one of them, but I can't tell this to Wasm engine. So I need a mutex, which is a no-op actually. But I need that's why it has the dereference. All right. So this is how it actually looks like. VFS plugin will be any resource. This will be VFS plugin will be my exported interface. And I have this resource absolute path. This is what happens. For every resource that you define, BindGen will create a trait which is host and the name of your resource. And as you can see, these are the methods that I declared on the resource. The methods are the same, so I just exemplified one. File name, it gets a resource of absolute path, even though I had an absolute path in the trait. Returns a string. You need to go into the table, get the resource, map it to a string, get it back. And make sure you implement this. So the engine will tell you when the resource has to be dropped, but it's your job to actually drop it. Your resource will live in a resource table. Unless you drop it, the resource table will keep the box over there. I was severely leaking memory on my first attempt. My downloads folder is 4,000 files. So this is how it looks like. This is how you manage resources. Step number 6. Now we have the host. So the host had to define an API crate, a trait that the other parts of the host can use to interact with the plugin, instantiate the executor, wasn't time. I skipped the code because it's long, but you can see it on GitHub, and manage its resources. Now we get to the plugin. Plugin is way easier. So for the plugin, you have cargo component, which takes the with file and generates your bindings, this bindings module. In this, you will find exactly the things that you have defined. Absolute path, the kind, the seek, the stat, and for every resource, you will find the trait. You can see guest file, which is the trait for the file, guest file system. Sorry, for every exported resource, you will find the trait, which is called guest, and the name. And then you will find this export macro. This looks pretty bad. I mean, if your user has to import these things from that package, not great. So this is an API crate. You create this for your plugin developers. You ship them a crate which glues this and exports nice types. And you need a macro for this. I mean, this macro is really bad, like types in bindings. No. I want an export VFS, type of the file system, type of the file, and initialization of my plugin. That's it. Problem. Cargo components generates the bindings, but the export macro is private. It's pub crate. For now, there's absolutely no flag that you can use. I haven't found one. It's manual modification in the file. That's why I can't use with bindings macro, because it generates behind the macro, and this export is private. I have no idea why they did this. I mean, I can't export it. You need to change 4 lines for this. And then you can write the plugin. Make a nice crate, import the crate that you have just defined, the WASM VFS in my case, create absolute path, export VFS, and the nice data types, which are the same as the ones defined in the with. You just implement for your whatever structure, local VFS, you implement file system, you implement file, and you go on. The read dir is exactly this. My plugin uses WASI P2, so no problem, it can interface with file system. You just write normal Rust code. And that's your plugin. I mean, just implement the interface, return whatever you want, whatever you need here, export it, use the macro. Plugins are straightforward. This is in Rust. And this one is in TypeScript. So it's the same plugin. GCO generates these type definitions. So as you can see, they're nice in JavaScript. It actually exports them nicely. As you can see, create absolute path is camel case, not snake case. And that's the VFS. I implement file system. I define this is my storage, FS. Read dir gets an absolute path, returns an array of absolute path, iterates over my file system, and the other 2 functions. And my file will look like, this. And then I just export them. I export the init function, which you need, file, and the data types. This is super straightforward in TypeScript. It was super easy. What I can't do in TypeScript is access the file system. Actually, I can, but you need to implement the glue code in JavaScript in between normal functions and whatever the WASI P2 backend exports. And that's shitty. I mean, you need to go low. But, I mean, you can do an SSHFS really easy because GCO has native support for web. So you can do requests super easily. And it's the same plugin in TypeScript. Cache them. It takes 5 to 30 seconds to compile these plugins. So whenever your app starts, it loads the modules and starts compiling. For Rust, not so bad, like 5 to 10 seconds, because basically the whole standard library is not in the component. Your WASM engine will supply to the component the standard library. It just has interfaces. Your component imports interfaces. But for JavaScript, it compiles the JavaScript engine. It takes a minute. So on your first start, no problem. The second start, you should start fast. So you just hash the file, check if your cache folder has that file. If so, just load it. And unsafe. Sadly, this is unsafe. When a module is compiled, WebAssembly is required to do a formal verification on the binary and to prove that it actually doesn't overflow or it doesn't do something stupid. But once it's compiled, the compiled thing is platform code. If it's M1, it's ARM. If it's x86, it's x86. So if you load a component which was serialized, WebAssembly can't guarantee anything. If somebody tampered this one, it can do whatever it wants with your computer. So whenever you cache, maybe digitally sign the binaries and verify them, or get somehow a verification here. So just as a fun fact. And with the caching, it starts in less than a second. No problem. So this is what actually we did. Junkyard was my main application. It had a crate which defined the host trait, so I can use it nicely. It has the WASM time engine crate, which was loading modules, and it was depending on the WASM component API crate. And the plugins were depending on that as well, on my plugin crate, and these were my two plugins. Compiled, all the three things were compiled separately. So, what are the lessons learned here? Tools are changing a lot. Documentation is sometimes not up to date. A lot of trial and error. Most probably, it won't change that much because the component model of Preview 2 is stabilized, so they need not change with files. Working with WASM time is not straightforward. Documentation is lacking. If you see an example, you can figure it out. If you don't see an example of what you want to do, you will struggle. Make sure you cache your plugins. I was shocked. The first time I started it, it was compiling 30 seconds. I didn't realize it compiles that much. I thought my computer was stuck or some infinite loop. I was Control-Cing, and then I realized, oh yeah, wait, this compiles. This is the biggest problem. WASM components are not native to Rust. Even though they have the WASI P2 backend, they still need to generate code that lifts and lowers your Rust types to basic WebAssembly types. I mean, numbers and pointers in a memory. It's standard, so the code is generated, but it's not native. What I would like to see is I define a Rust trait, I export the trait, I define a structure, I define an enum, and as soon as I hit export on my crate and say, okay, I want this as a WebAssembly component, it generates the with file for me. Or I get a with file, and the compiler is able to tell me, yes, it matches, no, this doesn't match. We're not there yet. So I don't want to have to take the with file, use a macro, adapt it. It's better than what we had before, but it's still not native. And if you look at the C code that it generates, it's, wow, horrible. It's not C++, it's C. Wow. Java is a little bit better. .NET, Go uses C code. It generates a C and a H file besides the Go. Tools are not able to generate symmetric traits, so I still need to adapt my trait if I want to use my plugin. Hopefully this changes. I'm confident this will be upstreamed at some point. And resource management is manual. They need a better thing. They need to do a better job. It wasn't time to manage these automatically. For now, it doesn't work quite automatically, but this is not a difficult problem to solve. So yeah, these are the lessons that I learned. My personal opinion is that if this takes off, this is the way that we are going to ship applications. It's a standard way to build components and a standard way to build plugins. The language in which we build them is irrelevant. Yes, JavaScript is slower, but if you have a JavaScript only with the engine, then you can ship components that just load the JavaScript. So you have really, really small plugins. You just need the plugin to run them. The language will not be an issue anymore. It's way better than DLL and SO files. So this was my presentation. Thank you so much. You can find the repository. If you have any questions, please. Yes?
Is it possible to create a plugin that's like a common library for? Thank you. Yeah, is it possible to create a plugin that can be called by other plugins, like a common library or something?
The question is if you can create a plugin that is called by other plugins.
Yeah, so you don't have to sort of distribute, let's say, the Java runtime. You can have that as a plugin and then have
Yes, this is the purpose of WebAssembly Components. So you create components, and because components export and import interfaces, you can link them together. This example is very, very simple, where you had the component and the host. But technically, you can compose components like you would compose functions in math. So you can even inject middle components. So you have a component that exports an interface, you want to tap it, you just put another component in the middle and do this. And you have the tools to combine components together or to link them separately, it depends, including graphical tools. There's a graphical component editor. I'll search it up. If you want, I'll search it up. But yes, this is the purpose. Distribute application as small components which are interchangeable, and technically your application becomes a component graph. So yes, that's the purpose. My example was a very limited example of what you can do with components to build plugins.
Any more questions?
Thank you for the presentation. My question is about async. If you have access to network, we want to run it efficient. So how async can be implemented in WebAssembly?
Thank you for the question. Question was, how does it work with async? So for preview number 2, async doesn't exist for the component. So if you want to do async within the component, it's going to ship Tokyo or some runtime with it. The calling interface from wasntime can be made async, but what actually happens is it will call, your function will be an asynchronous function, but the call is not going to be async. It's going to call a synchronous function, do a gas time, whenever gas runs out, if gas runs out, gas means WASM cycles. If gas runs out, it just suspends the engine, gives back control to whatever execution engine you have, Tokyo or Async STD or something, and asks it to be polled again. So right now, you can simulate async, but inside the component you need the executor, and outside of the component it just does gas counting. So it's not very efficient. Preview number 3, though, which is being worked now, is able to do this. I mean, they define streams, they define async functions, and this means that the executor, wasntime, is able to supply the executor to the component. So the component can actually export async functions. So it's in the work. I think Christoph here can give you more details, because I think he's working on that.
Thanks for the talk. My question is, what is the performance trade-off if you're pulling in the new style of components versus the one you showed at the start with the Zellij pipes? So what's the benefit for the components? How much of a performance trade-off is there? Because with WASM, we don't get the native CPU features like SIMD and other features like that. So what's the benefit over the previous model? Thank you.
So the question is, what's the benefit from core module to the components, right? All right. So you don't get, you might get the CPU features. So the WebAssembly language defines SIMD instructions. So if your compiler is able to generate them, the execution engine is responsible for translating them. So you might actually get, I think SIMD is available. And WebAssembly is adding new features to the language. Between the first and the second model, the first model had the problem it had to go through pipes. So what it needs to do is serialize the text into some kind of string, maybe with 0 characters, ship it to a pipe, and the plugin has to read it from the stdin from a pipe. That takes time. It's like chaining commands in bash. The second one shares data through memory directly. You don't have to go through the operating system. The execution engine defines a large static array, which is the memory of the component, and then just puts the information in the memory. But because you have a standard on how that information needs to be represented, for instance, strings are UTF-8 Rust encoding, then every component knows how to respect this. So you get a performance boost that you don't go through the operating system. And of course, you can link components together. With the core module, you just had functions exported. So this is the benefit. For speed, compared to native components, so for the large downloads folder, I had, after optimizations, 200 milliseconds for reading in a native plugin being compiled as a Rust crate. WebAssembly added 600 milliseconds for reading, like 1 second and a little bit was the time.
Can WASM components share memory at all, have proper shared memory, or do they need to copy every byte that they try to share between each other?
So basically, you can build a component by composing other components, and you have one single component. So that's where you share. In the component model, components don't share anything. They copy in between components. But if your component is composed out of several others, for instance, a JavaScript component, you have a component that supplies the code, or the pre-compiled JavaScript code, and you have another component that executes it. If you link them together, they share memory. But resources, on the other hand, resources live in the host. So when they handle resources, whatever, you just ship a number in between components. The actual resource lives in the host. This was one of the problems of the core modules. They couldn't share. They could, but bad things happen.
You mentioned earlier about async in the WASI stuff. Like, have you played with that at all? And like, what is its like, where is it along in the WASI stuff?
I don't know in WASI 3. Christoph here can answer your question better than I do, because he's working on that. For preview number 2, it's guess. I mean, guess, it just timeout. I mean, it just stops, allows others to do the job, and then continues. It's like a coroutine. It works like a coroutine.
So for the guest, so for the guest, the support is already merged. It's part of the bindgen.
Yeah, but guess, yes.
And for the host, they're currently working on it, and it's supposed to land within this quarter.
It's experimental, so it's not stabilized. Preview 2 is stabilized. Until this is not stabilized, even though it's nice, I would not recommend using it in production, because it might change.
Yeah, you mentioned that you needed to compile your plugin's AOT for performance reasons, because the time it takes to compile a plugin is prohibitive. Do you see that improving as WebAssembly compilers improve, that maybe we could switch over to just-in-time? Because as far as I'm concerned, your concern about plugin caches becoming modified being a security risk, that kind of invalidates all of the sandboxing. You know, I mean, you spoke about signing them, but obviously it's a massive reduction in sandbox security to compile them AOT. So do you see any work being done on the just-in-time compilers for WebAssembly that might mean that creating a cache might not be required in the future?
I think wasn't time can do both ahead of time compiling and just-in-time compiling. So I think you can enable it right now. Then it's gonna load fast, but execute slower, and compile gradually. So I think I speculate this, but as far as I know from the documentation, you can do this. And of course, there's different backends. I mean, wasm time is one. For instance, in Node or Dino, they do just-in-time. It loads instantly, and then it pays the price ongoing. One thing that probably you could do with ahead of time, use the TPM on your computer and actually digitally sign them. And yeah, the operating system needs to collaborate with you on that. But yes, you're right. But you can JIT it.
Any more questions? Nope.
Big round of applause for Alex for that excellent talk.